So we're a student club for computer vision and machine learning affiliated with U of T. And once a week, in the summer at least, we try to run paper discussions and conference style research orals. We'd also like to thank GitHub for sponsoring us, and you can scan the QR code here if you want to sign up for GitHub Student Developer Pack for free. Okay, thank you. Now, are you giving the?
Sure.
Yeah, now Rashid's gonna take over and discuss our paper for today, which is called Streetscapes.
So this is a paper that I had been reading and I thought was interesting. So yeah, this is what I'll be sharing about for today. And this is also a pretty recent paper, 25th July. And essentially they try to solve a very interesting problem. Uh, so so their problem is that you want to generate the Google Map style street views that you get. Uh, so if you go on like Google Maps, you always get like the street view, and then you can like go ahead or go behind and uh, almost like see a video from it. So they want to solve this problem, and the way they do this is uh, you uh, you get a street map. So this is the street map that you actually that a human or anything like gets you, and then you get a height map as well. Uh, so you know like how high buildings are, and so for instance, like they have this height map over here where this spot is really bright, so it should be the highest one. So on, just like relative height of all of them. So you have both of these inputs, and then you want to do and then you want to generate streetscapes like these. Uh, so so an interesting thing that they also do, which you see from the figure one, is they don't make this into a 3D generation problem, uh, which would be interesting because if you can like generate all of these individual 3D objects, you already have like all these segmentations over here, or like all the individual object outlines over here. So if you can generate individual 3D objects, you just need to place them around the map, and then you can do whatever you want. You want to do like this heavy snow thing or change lighting and that kind of stuff. It's very easy to do if you have like a 3D model and then you do 3D generation. Um, but they pose it into a very different problem. So they essentially make this into a video generation problem instead of 3D generation problem, uh, which is an interesting way to solve this. And they show that this comes with a few benefits over uh, just doing 3D generation, like 3D scene generation or 3D object generation. So so that's actually pretty interesting. Yeah, they they have a bit of well-written introduction. So maybe like we can go over some of it, and then maybe like just see all the figures.
Yeah, so the question, so basically as an input we have a map and the like this and the text description, but what the generated a stars and movements.
Yeah, you essentially want to generate like a full-scale video of the entire thing. Yeah, yeah. So unlike you would expect, there is no camera trajectory. So that's, I guess, slightly challenging, but you don't have control on like saying like, oh, this is like the camera trajectory or something like that. So uh, they talk a bit more about that later in the paper. I read it. I read the paper earlier once. Yeah, they talk a bit about that. So maybe we can also come to that. Uh, yeah. So So their intro starts with like input and outputs. So they talk about like the scene layout, which is an input, uh, and then the height map, which is also an input. So these are the inputs, and then you have the video outputs. So yeah, that's what they do, and they have these, and they also talk a bit about view consistency, which is, I guess, like very important for work like these, because you want to you want to somehow make sure that if you run like coil map or something on these kind of videos, then it should be uh, really perfect, just because there needs to be a very high geometric consistency among multiple frames of the video. So you also need to do this somehow. Yeah, so they have this G buffer thing, which yeah, let's they have a figure about that. So let's talk about that in the figure. And then they also have a autoregressive generation technique. Uh, so they still use diffusion, by the way. Uh, it's fu it's fully diffusion, but but they do but they do generation by parts. So you generate like two frames at a time, and then one more frame and one more frame, and then so on. So in that sense, it's autoregressive, even though it's like a diffusion model. Uh, sorry. Oh, yeah. I uh, so they build on top of stable diffusion. So yeah, it's just the stable diffusion backbone. Yeah. So yeah, and then they also talk about training data, which is a very important thing for them, because this is like really hard to collect training data, which looks like these. Fortunately for them, they have access to Google Maps training data, to all the Google Maps data, because some of them are apparently from Google. So yeah, they pretty much just describe over here that they use Google Maps or Google Street View, their mapping service data. So that's also, uh, I guess, like a bit interesting. Uh, yeah, they talk a bit about like related works where they talk about 3D object generation, uh, 3D scene generation, and then they also, I believe they also, yeah, then they also talk about video generation. Uh, so all of these are like pretty standard methods, pretty standard problems, and there are like a lot of approaches to do that. So we can like probably skip most of these, but they have an interesting paragraph here where they, in the related works, where they talk about like all of these unpublished recent works, which do uh, streetscapes generation. Uh, and I know like I know like some of these works, they were originally built with the motivation of solving like the self-driving problem or aiding the self-driving problem. So they do this with, I guess, like this motivation, but but they talk a bit about like these other methods for street view generation, and yeah, they talk about like Magic Drive, which is a very popular paper as well, and yeah, but essentially but as they say, like essentially what all of these other folks do is that you already have the 3D objects, and then you want to think about ways to place 3D objects, like do something with like streetscapes view generation, given you have the 3D objects and the 3D bounding boxes where the objects should be. So so that's like a problem all of these solve. And yeah, then they also talk about this other work which is very similar, and uh, and they also use text to video model. Uh, but but essentially, like what they do is slightly different. So uh, so they so as in like standard text to video models where you have like the cross frame attention and the V parameterization trick, they use both of those tricks and just use a standard text to video diffusion model. Uh, and they say that this is really problematic because you can never generate a large enough number of frames currently with this approach. So yeah, in that sense, I guess like they do like really interesting stuff. So yeah, let's maybe like talk a bit about like the method that they have. Uh, and Yeah, essentially like they have two main ingredients that they talk about, which are I guess like their two main contributions. So one is you have like this method on somehow conditioning on the scene layout, which is like one of their inputs. And the second is like this autoregressive method for video generation. And uh, these are like both of the things that they like roughly on a high level talk about. Yeah, they started like a background on diffusion models, but I think like you can like probably skip that because yeah, it's not like something in this paper, of course. So yeah, let's probably like skip that. Uh, yeah. So for the first part, which is like the layout condition scene generation, they have this figure. So let's probably try to go through this figure. So uh, yeah, uh, essentially we start with wait, let me go back to the figure. Yeah, so you essentially start with this model, which is a pre-trained uh, a pre-trained text to image model. So they just use stable diffusion as a text to image backbone. Uh, and yeah, they just use like stable diffusion for this as they talk about here. They talk a bit about like stable diffusion, but I guess like it's popular enough for us to skip it. Uh, yeah. So first they use like so first they have like this pre-trained backbone which is stable diffusion, and then they have this additional thing called a motion module. So so this is where I guess like most of their interesting stuff comes from. So so what you do is you have this motion module which is trained to generate two images at a minute. So at a point. So you parallelly generate two images at each time. Uh, and hopefully those two will be consistent enough and show some motion between them. The way they do this uh, is they they use these animation techniques. So particularly they talk about like how they uh, follow animate diff. So uh, essentially like what they do is so you have a sample I, which is probably ith frame, and I plus one, which is the I plus one frame. And then you want to train your model on and then you want to well not train the entire model but train just the motion module to parallelly denoise both of these frames at a given inference step. So uh, uh, yeah, that's what they do with parallel denoising. And and you can also like very easily take this motion module that you train and just use it within stable diffusion. So the motion module will need to be, if you think about it, like the motion module should be trained only on the streetscapes data because the original text to image diffusion model probably like doesn't have so many street views at all. Uh, So they also talk about this thing which is really interesting, that they don't retrain the stable diffusion model or like do a lot of fine tuning on it. And they say that uh, uh, even though like the stable diffusion model can't do this problem, it's really good to get the text mapping, and it already has a text mapping for all of these street view problems. It just can't solve them really well because it probably like doesn't have uh, it probably like doesn't have a lot of scenes of these kind of roads and uh, diverse roads and that kind of stuff. So it can't solve them properly, but it already has a text mapping for things like roads. Oh, oh, like do they find it in stable diffusion? Is that the question? No, no, they don't. They just build on top of it. Uh, yeah, yeah. Y- But yes, but so it's slightly different because so they don't, so they only have the thing like in the style of Barcelona or something as a text prompt. But all of the conditioning for generating the buildings and that kind of stuff, that doesn't come from text at all.
Yeah.
Yeah, and so that yeah, so they say that that could like probably be done by just stable diffusion. You don't need like anything more. Uh, yeah, for just those details. Yeah. So now they like have this motion module, and this allows them to do like parallel denoising. So now at each step, you end up generating two frames instead of one. Uh, and both of these frames are reasonably consistent because the motion module is trained on exactly this kind of data. Yeah. Then they talk about layout conditioning. Uh, so yeah, they so now you can generate two video frames, but you still want to like somehow incorporate the map and the height map, the both of the two of the inputs that you get, and uh, and they find that it's like super hard to write this as text just because like text is so sparse and that kind of stuff. So so what they do is they make these geometry buffers, which is also an interesting way of going about this problem because it makes sense uh, that you want to decouple the process of lighting and those kind of things with the texture, surface, and those kind of things. So all of these geometry buffers will only have like uh, texture, surface, and actual object things, and the lighting effects and that kind of stuff will be handled by the diffusion model, uh, like the actual generation process. So that makes sense, like why you would have like these geometry buffers to decouple both of those things. Uh, and yeah, then they talk about like how they do this. So yeah, particularly they say that you have like all of these different poses for ith frame and I+1th frame, uh, uh, which you get by just rendering both of these inputs, and and then you use these as conditioning using a control net style way of doing this. So that's how like they incorporate all of this conditioning from both the inputs that you get. Yeah, and then so that's about their layout condition generation. So finally with this what you get is two frames given both of your two inputs. So now they talk a bit about autoregressive video diffusion, and this is actually a pretty standard idea, the way they do this. So essentially, what they so they start by talking a bit about like color shift and those kind of problems, which video diffusion models always have. They're somewhat solved by like if you try to do the V parameterization trick, they are somewhat solved. Especially like color shift is somewhat solved for that. But they find but an interesting thing that they find is you you can like always so you anyways have control net, right? And it will allow you to condition on like whatever you want. So one technique is to like just take the frame that was just generated, pass it into control net for the next generation. And this is really problematic, as they say. It's really hard to like maintain the or maintain like a good level of consistency with this. So yeah, then they for this reason they start by talking about temporal imputation, uh, which is how they do autoregressive generation. So essentially, this is a quite simple idea, the temporal imputation thing. So you start by doing parallel denoising. Uh, you had like all of these C conditionings in the control net, and you also and then you made the G buffers by rendering it. Then you did the parallel denoising like they talked about in like the figure 2, and then you actually have two frames. Great. So now what you do is you do this thing that they call temporal imputation. So you so, so essentially what the model at a given so whenever you do parallel denoising yet again, what the model at that point as an oversimplified way of putting it thinks is that it already generated one of the frames, which was the frame that you just generated, and then it just has to generate one more frame. So an oversimplified way of putting it is that yeah, you just make the model think that, oh, it already generated this frame earlier. So that frame stays consistent. And then when you do parallel denoising, you only end up making one new frame instead of two new frames. So that's what they do for temporal imputation. And yeah, that's actually like a pretty simple way of doing it. But they say that it's still like it still doesn't require you to train any more new models, and it seems to be really effective for them. So yeah, that's an interesting way of putting it. And they also formalize this a bit, like how this formalization happens. So essentially, the main idea stems from you already generated a frame xi by parallel denoising. Then you generate a new frame xi plus 1. And to do this, you just make the model think that it already generated xi. So that's and then they formalize a bit. Uh, so so this is so essentially what they do is um, they don't uh, so whenever you are generating the next frame, you don't reuse the estimation, as they say. So they don't reuse the noisy estimation of xt. from the previous diffusion timestamp, and instead you just take the noisy estimate from the known frame. So that frame essentially you have like one frame that ends up being constant, and you just have to generate the second frame by doing all of these steps. Yeah. So that's what they talk about with this autoregressive video diffusion. And yeah, they in this they kind of like just formalize what I was talking about. Uh, yeah, and then they say that uh, so then they say that this also helps because even though like this is not perfect, like doing temporal imputation is not perfect, uh, but but you allow your but throughout the reverse diffusion, as they say, um, you have like slightly more noise, slightly less noise, and a slightly different features due to that which are being rendered. So this essentially is like very useful for them because yeah, it's just like making the training more robust. So it doesn't really matter if you have like all of these small differences while doing this temporal imputation. Yeah, and this allows them to like get consistency. Um, and then they talk about this other thing. Uh, so so to uh, so this parallel denoising and like this temporal imputation is already like gets them quite a lot of consistency with. But they talk about one more thing which allows them to further improve the consistency. So what they do is once you have the latent code for the I plus 1th frame, um, then what you do is uh, then what you do is like add a bit more noise to the previous time step and just rerun the imputation. So yeah, and as they say that this would just like this would just like help improve the consistency between both of them, uh, which makes sense, right? Because you're just doing this resampling again and uh, just making it more consistent. No, it's a bit different because, but I think like it's slightly analogous to like the CF, the classifier free guidance thing. Uh, so 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 whenever you're doing like whenever you find the score, well, we shouldn't say so. Whenever we find the Stein score, uh, when doing like the CFG thing, um, we don't need to like rerun this imputation stuff. Yeah, yeah. So that's like a big difference with like all of these ways of doing stuff, and you kind of need to do this for doing it this way because you can't like retrain the model, especially in like their setting. So yeah, you'll have to like do it this way, right? So yeah, and then they talk about another thing. So, popular technique and with all of these video generation models is that uh, let's say you already have a motion map or an optical map or whatever, and then you want to somehow condition the next frame generation on it. The way you do that is well, you just generated the optical map and you don't have the real frame because the real frame is what you will generate. So what you do is essentially you do very, very uh, naive warping and warp the current frame with that optical flow map or that motion map, then noise the warped image and the noising process. And because you are like noising all of it, you anyways like it doesn't matter if you have like weird artifacts or holes or that kind of stuff in the warped image. So you essentially then take this noisy warped image and then you pass it in as conditioning. And this is a really popular technique with most video generation models today. And and they also do this. So so what they do is uh, once you have like this known RGB image that you generate, you warp this image. Uh, so you have the so CI is the camera pose for the current view, and then CI plus one is the camera pose for the next view. So then you warp this image. And for this, you can use what they call the disparity map, which is available in the geometry buffer. So you have like this disparity map, which you rendered from the original inputs. So you just use this, warp the original frame, get a warped version of it, add noise to it, and pass that in as conditioning to the control net. So yeah, they talk a bit, they talk, where, where's that? Hey, yeah, never mind. And yeah, they also do this. And then they talk a bit about like how the warped image is not perfect. But I think like this part has already been very well shown. A lot of papers have shown that you don't need the warping to be perfect. It actually doesn't matter. If you warp it, if you do like very naive stuff or like just do stretching or whatever, it doesn't really matter. Uh, as long as you have like somehow the motion incorporated. So they talk a bit about this, but this has been like very well shown. So yeah, we can like skip through this about like how why warping works. So that's the process, and I, and they also so they talk about like most of the so they talk about like two of their main parts, which is the layout condition scene generation and auto-regressive diffusion. Um, and they also do like standard graphics techniques in the middle, like a big step of like being able to do this efficiently and being able to actually do experiments on this is they cull a lot of the objects in between, uh, which is a standard technique. So they also do like all of these standard 3D techniques yeah uh, throughout their pipeline. So yeah, then they talk a bit about like streetscape data. So this is the data they got from like Google Street View, and yeah, they essentially talk that they have like 1.5 million images from a few cities, and oh well, from a few countries, a few cities across 4 countries. Okay, so essentially they just have like all of these images that they collected. Uh, so yeah, it's I believe like all of these are like there's no interesting stuff in like how they generate the data. It's just that they already had it. So yeah, we can I guess skip past this and see like some of their results. Uh yeah, it's I guess like they have a few, yeah, maybe like you can see like a few qualitative results, and uh there were a few things that I noticed, and maybe I can show how that works. So yeah, they have a website which I think is like better to do this kind of stuff. Uh, yeah. So 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 an interesting part of what they show is if you do 3D reconstruction on this, which is the rightmost video, um, yeah, it's actually very good geometrically. And there's like a good amount of geometrical consistency between everything it generates, which you can see by the 3D reconstruction. There are like very few to no geometry artifacts with the 3D reconstruction. So I think that's like a really good part about what they try to do. Uh, However, like all of these priors are coming from a text to image model. Uh, so the main prior for how an image looks, given like all of these, is coming from a text to image model, which has like really uh, interesting problems that you would expect. So there's this video which I saw earlier today. Um, well, was it this one or this one? Yeah, okay. Probably I I don't know. I can't like seem to refine the video. But essentially there's this one video on the website which I was seeing like right before this. And because the priors are coming from text to image model, you still have some of these disappearing effects. So you have a car in the scene, and in the next frame, the car disappears. So you still have like those kind of effects, which aren't like fully solved yet with this approach. So uh, so that's also, I guess, like a bit interesting to observe. Uh, and I guess like another thing is that they also they also rely like quite a bit. So especially in their so they have like a few experiments where what they try to do is do infinite generation. So it just like keeps generating on and on. And I think like a very important step with this is to do like very aggressive culling. So you can just have so you can like just reasonably be able to run it on top of the pipeline that you have. Yeah, and then they also show a few comparisons with other methods of doing this. Uh, and yeah, I guess like the results are pretty interesting to take a look at.
This is those is really hard to use. Do you think it's slow or really hard? And it was a big about generation. Before um, okay, yeah, you're right. I think it's something like how does it go? Like some basis like the follow the so we don't really have this information about how this
Yeah. So that makes sense, and that's exactly why like you see many image generation artifacts in the video. Um, so especially like the video you were just talking about, like all the other objects. So if you try to see like a few of them, probably yeah, you see a floating tree here, right?
yes.
Yeah, and that's because it's a standard image generation artifact when you like try to do this kind of stuff. So uh, yeah, it's just like getting all of these informations from an image generation model. So yeah, yeah, that's probably like another reason why if you see the streets, the text is not good. It's like it's not like real letters, right? So yeah, that's also expected if you end up like using stable diffusion. So yeah, that makes sense too. Yeah. So yeah, this is what they talk about, and they also have a few quantitative results. So essentially, so it's I think it's like slightly it's not, these aren't like perfect methods to evaluate this kind of stuff because you aren't doing you aren't doing scene reproduction, so you don't want to end up with the same scene. Uh, if you like rerun it on the same map, you can like most certainly end up with a very different looking scene, and that's very much okay. You can have multiple ground truths for this kind of stuff, uh, by the nature of the problem, right? So, but they still show that they have like some interesting results for uh, perpetual generation and large scale generation of these kind of videos. So yeah, that's actually interesting to take a look at as well. That it seems to do these like pretty well. Uh, yeah, and then they have a few more examples which are quite interesting in their appendix. So so they have this thing where they can also do so because it's as much as just like adding text to the conditioning vector. So you can quite literally just add a text prompt. And so like they show you can do rainy day at sunrise or or even something else like yeah, this is the thing like in the style of Paris or whatever. Uh, and then it actually generates according to that. So yeah, you can also do this out of the box with their pipeline because just because you need to pass it in as a conditioning vector. Uh, so yeah, they also show this, and then they have and then they also have a few uh, other examples where yeah, where they talk a bit about like 3D reconstruction and four frame diffusion models. So, so they also talk a bit about this, and so essentially, instead of generating like two frames from the parallel denoising step, you end up generating four frames, and yeah, as I say, the temporal imputation uses the last two frames instead of the last one frame, and they say that this improves the consistency. Or so that's I guess like interesting to see as well. It's probably like significantly more expensive to do this, but yeah, they say that it seems to work very well. And then they also talk about like all of their 3D reconstruction. So as you can like probably make out from the 3D reconstruction video, it's a nerf. Yeah, there's like some very standard nerf. Yeah, just you can like see the video and say that it looks like it's rendered from a nerf. Uh, and yeah, they also talk about like for 3D reconstruction, they use the standard nerf pipeline. So you give it frames and you get the camera coordinate. You run call map, SFM, get the yeah, yeah. They pretty much like just use zip nerf, like the entire zip nerf pipeline to do this. Uh, yeah. So yeah, that's how they. And then they also talk about interpolation. So this is also a really popular way of doing like a long generation because so each step is like quite expensive and you're generating one frame at a step, and that requires like multiple like all of this things to do. So what people often do for video generation is that you generate start and end frames and then you interpolate between them, which is also a really popular way of doing that. So they also talk a bit about interpolation. uh, so yeah, and this allows them to like increase the frame rate by quite a bit. They say that yeah, they experimented with 3x frame rate increase. So yeah, that's pretty interesting. Uh, you can do like good level of interpolation from these. So that's I guess like good too. Uh, Yeah, and then they talk about like some of these problems as well uh, in their data. So so the data is also not perfect because you have many disparities with like yeah, as I say, like the boundary and the scene content doesn't always align very well with each other. So uh, yeah, yeah, you essentially have like uh, as they show over here, you have like this offset. I don't know what happened, but my screen went blank. Okay, never mind. Yeah, you essentially also have these offsets within the data, and uh, that becomes like uh, yeah, there isn't like proper data for some of these, and there's a lot of misalignment as well. They say that this is not a problem, and it just like the model somehow like gets over it, and it's just like robustness for the model. So yeah, they say that this isn't a big problem, but this is also prevalent in the data that they have. So yeah, so those are like I guess like some of the interesting things that they talk about, and yeah, then they also have like this appellation, and so so it is like quite expected that it's quite expected that resampling is that resampling is an important component of this, and they also show that warp the warpinate, what they call warpinate, the warping and then passing it and as conditioning is also really important. Uh, so they show that. I'm uh, I'm quite I don't know how to like I just a bit probably like confused about like how there's minus resampling gets good results on like a large number of like 16 to 32 and 32 to 64 frames. So I guess that's a bit puzzling, which is why I thought that this was interesting. This was an interesting table. Uh, yeah. Oh, y- yeah, yeah. So, uh, we are, uh, it's, I understand that it's like not the perfect metric for this kind of stuff, which makes sense because it's just like measuring image similarity at the end of the day. So, so it's not perfect, but I guess like that's the thing that every yeah. So, but like that's what you can I guess like try out. Uh, and there are like very few metrics that actually make sense for this kind of stuff. So
Yeah, it's
yeah,
your entire system.
yeah, exactly. Uh, so yeah, so yeah, that's about the paper.